Hello everyone, good afternoon. It's my pleasure today to welcome Sachin Kadi. Sachin is currently a postdoc at Berkeley working with Scott Schenker. Before that he completed his doctorate at MIT working with Dina Katabi. His interests run the gamut through network systems, communications, security and information theory. Today he's going to tell us about some of his thesis work. And in that work, he's looked at the concept of network coding and how that affects the design of wireless networks. This is work for which his dissertation was awarded the Sproul's Award at MIT. That's the award for the top ECS doctoral thesis. And so without further ado, Sachin.
Thank you. Thanks for the generous introduction. So today I'm going to talk about the network-coded wireless architecture for wireless mesh networks. But first, what are wireless mesh networks? Unlike traditional centralized access point or cellular networks, wireless networks are decentralized multi-hop networks of wireless links. So typically, you would deploy wireless routers around a city like in this picture, and they would automatically discover and connect with each other to form a mesh network and provide connectivity from any node to any other node. So as you can tell, these networks have great properties. First, they give you blanket coverage at very low deployment and maintenance costs. And they have already been deployed in a variety of research and commercial settings and will probably get deployed much more in the future. But they are also intellectually very appealing because the fundamental performance limits on these networks are unknown. The performance of these networks in practice is hampered by the challenges posed by the inherent characteristics of the wireless medium. First, the wireless medium is a shared broadcast medium. So this means that in a dense wireless mesh network, where there are multiple devices competing for access to the medium, all of them have to be routed through the same shared medium, which drastically reduces throughput. Second, the broadcast nature creates interference among neighboring transmissions. Typically, wireless mesh networks have dealt with interference using very conservative scheduling protocols to avoid interference at all costs. And this further reduces throughput. So in this talk, I'll take the opposite approach. Instead of dealing with the broadcast nature and interference as challenges to be dealt with, I will show you how you can turn them into opportunities which you can exploit to significantly increase network throughput. So here are two people, David and Sumit, and they want to talk to each other, but they are not within wireless range of each other. So they're going to use this router in the middle to relay their packets. So I'm going to use this simple example throughout the talk to demonstrate the different ideas. But the techniques themselves generalize to arbitrary topologies and arbitrary flows. So let's see how David and Sumit can talk to each other. So David takes his packet, sends it to the router, who forwards it to Sumit. And Sumit takes his packet, sends it to the router, who forwards it to David. Very simple stuff. In total, you needed 4 time slots to get these 2 packets across. But David and Sumit are very smart people. They want to do better than 4 time slots. Can they do it in fewer time slots? So here's our approach. So David takes his packet, sends it to the router. Sumit takes his packet, sends it to the router. Here's the key difference. Instead of the router transmitting these 2 packets separately, he combines them using bitwise XOR to create a single coded packet of the same length and broadcasts that coded packet to David and Sumit. Now remember, David already has the red packet he sent earlier. He can XOR it with the coded packet he just received to recover Sumit's packet. And Sumit can repeat the same process and decode David's packet. So now, instead of 4 time slots, you needed only 3 time slots to get these 2 packets across. And the fewer time slots automatically leads to higher throughput. But this example is a bit awkward. How often do you find that there are two flows which are exactly in the opposite directions of each other. Is this approach limited only to this very simple example? It's not, and it actually generalizes to arbitrary flows. So let me show you through a different example. Here, there are two flows again, but S1 is sending traffic to D1 through the router in the middle, and S2 is sending traffic to D2 through the router in the middle. So you have two flows that intersect at a router. Now, S1 takes this packet and broadcasts it to the router. Because of the broadcast nature, D2 overhears this packet. In the current design, D2 is forced to throw away this packet because it's not meant for it. Instead, we let D2 keep this packet for a short amount of time in our approach. Similarly, S2 takes this packet and broadcasts it to the router. D1 overhears this packet and keeps it for a short amount of time. Now, again, the router does the same thing as before. Instead of transmitting these two packets separately, he exhorts them to create a single coded packet and broadcasts that coded packet to D1 and D2. Now remember, D2 has overheard one of the components of this coded packet. So again, he can just XOR and get the packet actually intended for him. And similarly, D1 can repeat the same process and get the read packet intended for him. So instead of 4 time slots, again, you needed only 3 time slots to get these two packets across, leading to higher throughput. Yes?
Just a quick question. Would there be any acknowledgement in this? So how does one know that the other received the packet?
Yes. So the question is, will there be any feedback about what packets have been overheard? That's a great question, and I'm going to come to it in exactly 5 slides. All right? But there's a more fundamental point here. The shared broadcast nature of wireless actually creates opportunities where you can apply this coding approach and improve throughput. And this generalizes to arbitrary flows and topologies. Typically, the example I just showed you is part of a larger network. And in this network, whenever router has packets to transmit and an opportunity to transmit on the wireless medium, he's going to look for opportunities to apply our approach, reduce the number of transmissions, and maximize network throughput. But let's reflect on what we actually changed about the network design here itself. So instead of dealing with the broadcast nature of wireless by imposing an artificial point-to-point abstraction on it, we are now exploiting the broadcast nature of wireless to increase network throughput. Second, instead of the routers simply storing and forwarding packets like in traditional networks, you now give routers the ability to mix the contents of packets before forwarding them. That is, perform network coding on packets. Now, network coding has a large body of theoretical work behind it. But this particular work differs from all that work in 2 important respects. First, it addresses unicast traffic, where a single source is sending traffic to a single destination, and there are many such unique flows in the network. Prior work on network coding was focused on multicast traffic, where a single source is sending the same traffic to multiple destinations. And the unicast is the common case found in the internet. Second, this work makes no assumptions about the environment. It works in dynamic environments, does not assume any knowledge about the topology or the traffic demands. Prior work in network coding assumed that you had perfect knowledge about the topology as well as the traffic demands that existed in this network. So we built this system into a system we call COPE, and let me go through the design of COPE in the next few slides. So the first component of COPE is snooping. So remember, we want to exploit the broadcast nature of wireless. So to do that, we make every node snoop on all the packets transmitted on the medium. And when a node overhears a packet, he stores it for a short amount of time. So here, the red node is transmitting a packet to the blue node. When he broadcasts it, the green node overhears this packet and stores it in his oval storage area for a short amount of time. Now here's the fundamental question of COPE. How do you code packets? So let's take a step back. Suppose we have a packet P, which we need to send to a neighbor A. A naive approach is to XOR this packet P with other packets already known to this neighbor A. This will ensure that A can decode that packet. But what did we achieve by this? We had one packet which we needed to send to A. We might as well have sent it without coding that packet. COPE is only going to be useful if we can benefit multiple neighbors from a single transmission. So let's develop the intuition through a slightly more complicated example. Here there's a router D. He has 4 packets sitting in his queue, and they are headed to the 3 next hops A, B, and C. The color of the arrow indicates the direction of the correspondingly colored packet. So the red packet is headed to A, for example. Now these next hops have also overheard some of these packets from prior transmissions and have kept them in their storage areas. So let's look at D's options and how he can code packets together. So suppose D XORs the yellow and the red packets together to create a single coded packet. The yellow packet is headed to C. C has the red packet in his storage area, so he can decode and get the packet intended for him. But unfortunately, the red packet is headed to A, and A does not have the yellow packet to decode. So this is a bad coding decision because you benefited only one neighbor from one transmission. You didn't get any throughput improvement. What if D XORs the blue and the red packets together to create a single coded packet? The blue packet is headed to C. C has the red packet, so he can decode. And in this case, A has the blue packet in his storage area. So he can decode and get the packet intended for him. So this is a better coding decision because you benefited 2 neighbors from one single transmission, nearly doubling the throughput. But can we do even better than that? Can we benefit all 3 neighbors from one single transmission? What if D XORs the red, the green, and the blue packets together to create one coded packet? The red packet is headed to A. A has the other 2 packets, so he can decode. And similarly, B and C have the other 2 packets apart from the packet intended for him. So they can decode and get back the packets they want. So this is the best coding decision in this particular example. So you benefited all 3 neighbors from one single transmission, nearly tripling the throughput. But this also gives us insight into what is the constraint on coding and decoding packets. A router can XOR n packets together if and only if the next hop of each packet already has the other n-1 packets apart from the one it actually wants. Now, at first sight, this seems like a very onerous constraint. How often do you find that this constraint is satisfied in mesh networks? In fact, it's quite frequent. So to see why, let's look at this example. The red packet is probably headed from the bottom towards A, and when it is transmitted, B and C overhear this packet. Similarly, the green packet is probably headed from the top towards B, and when it is transmitted in prior transmissions, A and C overhear this packet. And similarly for the blue packet, which is headed from the right towards C, A and B overhear this packet. So you often find these scenarios in mesh networks where your next hops have overheard a bunch of these packets, and you can apply the COPE coding technique to minimize transmissions and improve throughput. So let's get back to Chris' question. So I made an assumption here that the router knows exactly what packets the neighbors have to make the right coding decision. How does the router know neighbors' packets? The idea is to use guessing. So the router guesses if a particular neighbor has overheard a specific packet. And the way it guesses is to use the packet delivery rate measurement between the previous hop of that packet and that particular neighbor. And the nice thing is this data is already available from the routing protocol. So typically, mesh networks run a link state protocol where these measurements are taken every few seconds and distributed throughout the network. And the router uses this data to guess what is the probability that a particular neighbor has overheard a particular packet. So in this example, the blue node can guess if the green node has overheard this red packet by using the packet delivery rate between the red and the green nodes. So here's the formal statement of the problem. A router has n packets, and each of his next hops has a different subset of these packets already overheard and wants a specific subset. And the router has to deliver these n packets using the minimum number of transmissions subject to coding constraints. And here's the intuition beyond the solution. So at every router, we construct a virtual graph. And in this virtual graph, each packet queued up in the router is a vertex, and 2 vertices are connected if the corresponding packets can be coded together. So again, in our example, the router has 4 packets, so there are 4 vertices in this virtual graph. And what are the edges in this virtual graph? The red and the blue packets can be coded together, so you can connect them by an edge. Similarly for red and green, and so on for the rest of the graph. Now here's the key bit. Notice that a coded packet is a click in this virtual graph. So from this pairwise graph construction, you can show that any coded packet, even 3 or 4 packets, corresponds to a click in this virtual graph. So minimizing the number of transmissions using coding corresponds to partitioning this virtual graph with a minimal number of clicks. And click partitioning itself reduces to graph coloring in the complement of this virtual graph. Now we all know graph coloring is NP hard, so we use a heuristic solution in the paper. But this intuition is pointing at something, a more fundamental connection. So you can make this intuitive argument precise to show that the coding problem in COPE is functionally equivalent to graph coloring. And you can use a separate argument to show that the coding problem in COPE is functionally equivalent to the open problem in information theory of finding the network capacity with network coding. And thus, the coding problem in COPE allows us to connect an open problem in information theory with an equally important problem in CS theory. And any techniques developed for any one of these problems can now immediately be applied to the other two. This solution also meets some nice practical characteristics. So first, the coding algorithm is opportunistic. It codes packets if possible. But if there are no coding opportunities, it forwards these packets without coding them. So suppose a packet is at the head of the queue. The router checks if it can sneak some other packet by coding it with this packet. But if there is no such opportunity, it just sends that packet without coding that packet. So we do not intentionally delay packets to improve coding opportunities. And this ensures that COPE works with existing applications. Second, the implementation complexity of COPE is quite small. We are using simple bitwise XORs for coding and decoding packets. So this is very efficient to implement. Finally, COPE is architecturally clean. It sits transparently between the IP and the link layers and does not require any modifications of these layers. So COPE is plug and play, and you can put it in the current network stack itself. So we implemented COPE in Linux using the Click software router. And the current implementation of COPE works with 802.11 radios. But the idea of COPE itself is independent of the underlying radio technology. So we deployed it using the RoofNet platform, and the routing algorithm we compare it against is based on the same RoofNet mesh platform. So how does COPE perform in practice? So let's go back to the same example, David and Sumit talking to each other, and let's see what are the performance improvements we get for this simple topology. So intuitively, we saw that we needed 3 transmissions instead of 4 to get these 2 packets across. So we are expecting a 33% improvement in throughput. But here are results from actual experiments. On the x-axis are the different 802.11 bit rates. And the y-axis is the throughput gain obtained by COPE compared to the current approach. So as you can see, COPE nearly doubles the throughput. Instead of 33%, you're getting 80 to 90% throughput improvement. Now this is very surprising because the experimental results are beating the theoretical prediction itself. What's going on? So it turns out there is a very subtle connection between the network coding technique and the underlying link layer protocol running in 802.11. The 802.11 MAC is fair. The MAC is the link layer. The 802.11 MAC is fair. So when there are 3 nodes contending for the medium, it divides access to the medium equally among all 3 nodes. So there is 1/3 allocated to each of these nodes in this current setting. So this means that without COPE, for every packet David and Sumit transmit, the router has to transmit 2 packets out. But he's only getting 1 time slot in every 3 time slots to transmit a packet out. So there is a mismatch between what the link layer is allocating to this router and the amount of congestion at this node. But with COPE, all nodes need equal rate because the router needs to only transmit 1 coded packet for every packet David and Sumit transmit. So COPE significantly improves throughput because it alleviates the mismatch between the max capacity allocation and the congestion level at this node. So we went ahead and studied what are the fundamental limits on these gains for arbitrary graphs. So as you can see, there are two different kinds of gains, coding gain and the coding plus MAC gain. The coding gain is defined as the reduction in the number of transmissions which we get with network coding. And for the David-Sumit example, you saw that the coding gain is 4 by 3, 1.33. But the coding plus MAC gain is defined as the improvement in the draining rate at the bottleneck node due to network coding. For the same example, the coding plus MAC gain is a factor of 2 because the router's queue now drains twice as fast compared to without network coding. And you can so the coding gain reflects gains when the network is not congested and the nodes are not backlogged. And the coding plus MAC gain is more apparent when the network is congested and the nodes themselves are backlogged. So you can show that for random planar networks under the protocol communication model, the coding gain is bounded by a factor of 3. So you can get at most a 3x throughput improvement for random networks. But the coding plus MAC gain can be unbounded. Now this is a very surprising result, but the way you show it is by constructing an arbitrary network such that the router is arbitrarily backlogged without coding, and the gain from coding can be arbitrarily large. Now in practice, you are not going to see such huge gains. You're going to see smaller gains, but still the coding plus MAC gain is going to be significantly higher than the coding gain. And these gains are reflected in the large-scale experiments with COPE. So we deployed a wireless testbed of 20 nodes spanning 3 floors, and this is how we run the experiments. So we pick a sender and receiver pair at random, and we start UDP traffic between them. And the flows themselves arrive according to a Poisson process. And the size of the flow is taken from empirical internet measurements. So here's a picture of the testbed. This spans 3 floors in our department. And the only takeaway point here is nodes were placed where there was an opportunity to. And so there's a lot of diversity in the links in the, between nodes. So here are results from actual experiments. On the x-axis is the total demand placed on this network in megabits per second. And the y-axis is the total network throughput obtained by different approaches. So as you can see, COPE provides nearly a 3-fold throughput increase over the current approach in congested networks. But the more interesting point about this graph are the two sides to it. So when the network is not congested, the nodes are not backlogged, and you are seeing smaller gains. And this corresponds to the coding gain we just defined. But as the network gets congested, the routers get more and more backlogged, and the gains you see are more reflective of the coding plus MAC gain we just defined. Now you might be wondering, why are both these curves tapering off as network congestion increases? So this has got nothing to do with coding itself. It's more a function of the 8/11 link layer protocol. It doesn't do a very good job of allocating access to the medium when the network gets heavily congested, and both approaches taper off. But COPE still provides nearly a 2 to 3x throughput increase over the current approach, even in that extreme case. Sure.
So if the MAC gain is unbounded,
Yeah.
why weren't you working on MAC?
So that's exactly what's the next part of the talk. So how do you fix the MAC for? So we saw that with traditional forwarding, these two guys required 4 time slots to get these 2 packets across. But with COPE, you needed only 3 time slots due to network coding. But they are ambitious people. They are not happy with 3 time slots. Can they do it in 2 time slots? If you take a step back and think about this, why not exploit the fact that the wireless channel naturally mixes signals when packets interfere? Why not perform network coding on analog signals themselves? So let me again demonstrate through the same example. So David and Sumit are sending packets to each other, but now we are representing the packets with the actual signals they are transmitting on the medium. Here's the key difference. Instead of transmitting these packets separately, David and Sumit are going to transmit simultaneously. So because the packets collide, the router receives an interfered signal. He cannot make any sense out of it, but he doesn't even try to. He just re-amplifies and broadcasts this interfered signal to David and Sumit. Now remember, David already has the packet he sent earlier. He can transform it into its signal representation, subtract it, and get back Sumit's signal. And then he can use standard decoding methods to get back Sumit's packet. And similarly, Sumit can repeat the same process and get back David's packet. So in total, now we needed only 2 time slots to get these 2 packets across, leading to even higher throughput. Now, as you can guess, I'm hiding a lot of details under the rug here. There's a lot of engineering to be done to subtract these signals correctly. But before I get into those details, let me talk about the main contributions of analog network coding. First, analog network coding advocates a philosophical shift in the way we deal with interference. Traditionally, wireless mesh networks have used very conservative scheduling protocols to avoid interference at all costs. Instead, we show that we can strategically exploit interference to actually increase network throughput. And this promises new ways of dealing with the hidden terminal problem. So what is the hidden terminal problem? David and Sumit are classic examples of hidden terminals. They cannot sense when they are transmitting and often end up transmitting simultaneously and colliding. And there's a lot of research done to make sure they do not transmit simultaneously. But as this example just showed, let them transmit simultaneously. That actually increases your network throughput. And second, analog network coding introduced a new notion of network coding. Instead of mixing packets, now we are letting the wireless channel mix signals for us, and the routers are simply amplifying and forwarding these signals. So how do we make analog network coding work in practice? So as I said, subtracting signals is not that easy. And the reason is, interfered signal is not exactly the sum of these 2 signals. The wireless channel distorts these signals. And not only that, it's almost impossible to ensure that David and Sumit start transmitting at exactly the same time. There is always going to be some asynchrony between these 2 nodes. So what you get is not the sum of 2 signals, but the sum of distorted and time-shifted versions of these signals. And you have to decode a packet out of this distorted signal. So when we started work on this problem, our first reaction was to see if we could get these 2 nodes to be synchronized. Can we get David and Sumit to transmit at exactly the same time? As you can tell, it's impossible to do that. It's very, very hard. So instead, it turns out asynchrony is a blessing in disguise. So let's say David starts transmitting before Sumit does. So there is some amount of asynchrony between these 2 nodes. And what that results at the signal level is this small interference-free part at the start and at the end. So because David started transmitting slightly before Sumit did. So you can use this interference-free parts to estimate the amount of distortion the channel is applying on your signal, as well as the amount of asynchrony that exists between these 2 nodes. And once you have these estimates, David can apply it to his known signal, compensate for them, and then subtract it from the interfering signal. And once he has that, he can decode Sumit's packet. What does Sumit do? Sumit does the same thing, but runs the same algorithm backwards. So analog network coding exploits asynchrony to make it practical. So how do we build this protocol in practice? So let me just go through the different steps, and then I'll get to the decoding algorithm. So first, the router senses whether the wireless medium is idle, and then broadcasts a short trigger to David and Sumit. Once these 2 nodes receive the trigger, they jitter their start times by a small random amount and then transmit. Because they transmit simultaneously, the packets interfere, and the router receives an interfered signal. He amplifies and forwards this interfered signal. And now, David and Sumit receive and decode this interfered signal. So this is the key step. So how do David and Sumit decode this interfered signal? So analog network coding works with any modulation scheme. And it includes components for accurate channel, frequency, and sampling offset estimation in the presence of interference. These are iterative algorithms which work despite interference. Second, the decoding complexity of this algorithm is linear. And it has been implemented in software radios for a number of modulation schemes. But today, for pedagogical reasons, I'm going to describe it in terms of MSK and assume that the frequency and sampling offsets have already been estimated and applied to the known signal. But if anyone's interested, I'm happy to talk about these components offline. So before I go to the decoding algorithm, let's get a quick primer on modulation and demodulation of wireless signals.
So this trigger, is that a Mac hack or is it some other Mac?
It's essentially a simple MAC protocol for this particular topology. The router is trying to control who is sending simultaneously and who is not.
But it's still a dot level node.
It's still at the MAC level. The router is trying to do this.
Okay, but your nodes are all dot level nodes.
Yes.
So it's still running at dot level.
Yes.
There's something on
You mean is there something?
the router.
Oh, it's still running on the router, yeah.
So when the router is going to send this trigger, is this going to be much less overhead than the router actually sending an extra packet?
Yeah, the trigger is very, very short. It's 1% of the packet size or something. So it's it's negligible overhead. So before I get into the decoding algorithm, let me give a quick primer on modulation and demodulation of wireless signals. So as in any digital communication system, you can represent a real signal using samples. And just trust me on this, wireless signals can be represented using complex samples. And since, as I said, I'm going to focus on MSK, which stands for minimum shift keying modulation scheme. So the way MSK signals bits is by angles between consecutive complex numbers it transmits on the wireless channel. So suppose you wanted to transmit bit 1, you first transmit this complex number D1, and then transmit a second complex number D2, which leads D1 by 90 degrees. If you wanted to transmit bit 0, you first transmit D1, and then D2, which lags D1 by 90 degrees. So from now on, I'm going to assume David wanted to transmit bit 1. So he takes these two complex numbers D1 and D2 and transmits them on the wireless channel. But the wireless channel attenuates these complex numbers by a random amount. The nice thing is it's by the same random amount. So D2 and D1 are roughly attenuated by the same amount. But the wireless channel is even more nastier. Not only does it attenuate these complex numbers, it also rotates them by a random amount. But again, the key property is the angle between consecutive complex numbers is preserved because the rotation for both these complex numbers is by the same amount. So to decode, what a node has to do is compute the angle between consecutive received complex numbers. In this case, it is 90 degrees, and he knows bit 1 was transmitted. So that's it. That's how MSK modulation and demodulation works. Let's get back. So let's get back to the problem at hand. How does David decode this packet? So remember, the red signal is David's signal, and the blue signal is Sumit's. So as you can see, there is a small uninterfered part at the start. So David decodes this using standard MSK demodulation. Now when he reaches the interfered part, he notices that there is a large variation in the energy he is seeing in the signal. So he declares interference and then switches his decoding algorithm. This is the key contribution of analog network coding, and let me zoom in detail as what's going on here. So what did David send? He sent these two complex numbers, D1 and D2, where D2 is leading D1 by 90 degrees. But after they went to the channel, they got attenuated and rotated. And David does not know what happened to his complex numbers after going through the channel. So what did Sumit send? Let's say he wanted to transmit bit 0. So he transmits two complex numbers S1 and S2, but S2 is lagging S1 by 90 degrees. And after they go through the channel, they too get attenuated and rotated by unknown amounts. So because these signals were transmitted simultaneously, they interfere. And interference can be modeled as complex addition. So D1 and S1 add up to produce X1, and D2 and S2 add up to produce X2. But what does David know at this stage? He definitely knows what complex numbers he transmitted and what is the angle between these complex numbers. And he also knows X1 and X2, because those are the complex numbers he actually received. But he does not know what happened to his complex numbers after they went to the wireless channel. And he definitely does not know what Sumit sent. If he did, he already knows what bit Sumit transmitted. So this is all he knows, what he transmitted and what he just received. But remember, he also has this interfered signal, which is interference free at the start and interference free at the end. So he can look at the complex numbers in this part, estimate their amplitude alpha, and he knows that his complex numbers have to lie on this red circle of radius alpha. Similarly, he can look at the complex numbers at the end of this interfered signal, that corresponds to Sumit's signal, estimate their amplitude beta, and he knows his complex numbers have to lie on this blue circle of radius beta. So now he has two additional constraints, and he has to figure out what complex numbers could have added up to produce x1 and x2. So you can show this formally. So suppose this is the complex number. You can show that the angles of these complex numbers can take two solutions. So don't get scared by the math. You can show this very visually. So what this means is when David solves for x1 and x2, he gets two solutions. There's d1 and s1, which could have added up to produce x1. And there's a symmetric second solution, d1 prime and s1 prime, which could have added up to produce x1. Similarly, for x2, there is d2 and s2, and a symmetric second solution, d2 prime and s2 prime, which could have added up to produce x2. So you have two solutions for each interfered complex sample. And this confuses David, because now there are four possible angles between consecutive complex numbers. There's the angle between d1 and d2, d1 and d2 prime, d1 prime and d2, and d1 prime and d2 prime. What's the correct angle? So remember, David knows the angle between his complex numbers. And he also knows that the wireless channel preserves this angle. In this case, it's plus 90 degrees. So all he has to do is pick the set of complex numbers which have the same angle. And in this case, it's d1 and d2 with an angle of 90 degrees between them. And this automatically dictates the choice for Sumit's complex numbers. And once he knows s1 and s2, he's home free. All he has to do is find the angle between these two complex numbers. He knows it is minus 90 degrees, and he knows Sumit transmitted bit 0. So he has managed to decode Sumit's bit. And he repeats this process for the rest of the interfered signal, again until he reaches an interference-free part. And there he decodes using standard MSK demodulation. So what does Sumit do? Sumit repeats the same process, but backwards, to decode David's packet. Now I've described this example again using the 3-node topology, but this generalizes to other topologies, such as the chain topology where S is sending traffic to D, and even if there is a single flow in the network. COPE does not apply in this case. It also applies to the cross topology we saw with COPE and other similar topologies we found in COPE itself. So how does analog network coding perform in practice? So we built analog network coding using GNU Radio software radios. And the radio we've used is the USRP frontend, which looks like this. And we deployed analog network coding in the ISM band, the 2.4 to 2.48 gigahertz frequency range, in a 25-node testbed. And we evaluated analog network coding for common scenarios found in wireless mesh networks. But today I'm going to show you results only from the David Sumit example. There are many other results in the paper itself. So as we saw, intuitively we expect that the throughput gain of analog network coding over the current approach is a factor of 2, and 50% over COPE, because we went to 2 time slots from 3 time slots. And you can go ahead and show formally what are the gains as the wireless SNR varies. So for a symmetric two-way relay channel, which is what the David Sumit example is, you can find an outer bound on the routing approach, which is the current approach, and what is the rate achieved by analog network coding. So what this analysis tells you is that at medium to high SNR, ANC doubles the actual network throughput. But at low SNR, ANC can perform worse because you're re-amplifying noise at the router. So at low SNR, you actually use multiple access techniques to get the same performance, to build this network. But at medium to high SNR, which is the common case in indoor networks, 8/11 networks, you can use analog network coding to double your throughput. So here are results from actual experiments. So this is over 3-node topologies, which we find in our 25-node testbed. On the x-axis is the throughput gain, and the y-axis is the cumulative distribution function of these throughput gains over these different topologies. So as you can see, the median throughput gain over routing is 70%, slightly less than the 2x we were expecting. There are two components for this reduction. First, if you want the exact 2x gain, we have to get these two nodes to be perfectly synchronized. That's how you get the 2x gain. But remember, we need asynchrony to make analog network coding practical. So we lose some part of the gain due to this asynchrony. Second, the decoding algorithm in analog network coding is not perfect. It introduces a slightly higher bit error rate. So you need more redundancy to correct those bit errors, and that contributes to a further reduction in the throughput gain. So what you get is 70%. Yes?
So for this protocol, can you only have two senders? Can you have multiple senders, but everybody has to hear all but one? What's the rules on what you can do?
So you can have more than two, but it gets very hard to scale it after 3 or 4 packets. The reason is just the way these things interfere and what is the dynamic range of the ADC itself on these radios. If you have many signals interfering, it's very hard to distinguish these different signals. So the way you think about this protocol is, I have a substrate which can now take apart 2, 3, or 4 signals. How do I design the MAC protocol to take advantage of this substrate? So the MAC protocol has to make sure that the right number of nodes interfere, and then you can use analog network coding to decode these interfered signals.
And do you also need to have everyone who's working in a given area know all but one of the people sending there? Or can you have more than one unknown?
In the current description, yes, but you can have another technique where you get a second interfered signal, and you can combine these two interfered signals to take them apart, even though you don't have any signals in advance itself. So there's subsequent work, which is not my work, which has extended this technique for that case. And what's the throughput gain over COPE? So you get a median gain of 30% compared to the 50% we were expecting in theory. Again, the reduction is due to the same two reasons, the asynchrony and the slightly higher redundancy we need to decode these packets. So as you can tell, this work builds on important work in 2 areas. First is network coding theory. There's a large body of work which shows that network coding can achieve the multicast capacity of networks using linear, distributed, and polynomial time codes. Second, there is an important set of work in building robust and efficient mesh networks at a number of universities and research labs. But when we started this work, these 2 areas were separate. This work bridges these 2 areas. It makes contributions to both and shows that there is an inherent synergy between them. So here are the contributions to network coding. This work provided the algorithmic framework for using network coding in modern wireless networks. Specifically, it designed new algorithms for using network coding in unicast traffic, where there is a single source sending traffic to a specific destination, and there are many such flows in the network. This is the common case in the internet. Prior work was focused on multicast traffic. Second, it works in dynamic and unknown environments and makes no assumptions about the network topology or the global traffic demands. Prior work made these assumptions. Finally, it provided the first implementation of network coding, deployed it in a testbed, and showed that network coding can deliver large throughput gains in practice. And here are the contributions to wireless mesh networks. This work showed that network coding provides a systematic framework for designing wireless mesh networks which work with and exploit the inherent characteristics of the wireless medium to increase network throughput. It designed a packet-level network coding technique to exploit the shared broadcast nature of wireless. It designed an analog network coding technique to exploit strategic interference and increase performance. And third technique, symbol-level network coding, which I didn't have a chance to go into detail today, which teases out the correct bits in a corrected packet and funnels them such that it can deliver a correct packet end-to-end and significantly improve throughput. All these techniques were deployed in a testbed, and shown to deliver a several-fold increase in throughput. So here's my conclusion, and I'm happy to take any more questions. Thanks. Yes.
The analog network coding seems very similar to approaches used in sort of traditional CDMA style networks or CDMA style communication, are there key distinctions, or I mean, aside from the common key? Or
So the fundamental difference is analog network coding is exploiting known side information. So the side information here was in the form of known packets one of the nodes already knew. And in CDMA, you don't have that. Both of these packets are unknown to the receiver, and they have to be decoded from this. Because you can exploit side information, you can achieve much higher throughput than the CDMA approach. And that's exactly where the theoretical analysis came in. We can show that you get 2x throughput gain at medium to high SNR compared to a CDMA-based approach.
Go ahead, John.
I can't see you guys.
In the testbed results, did you artificially constrain the situation some way? For instance, were they all transmitting at the same bit rate? Were packets all maximally sized?
So the packets were all of the same size, 1500 bytes, which is the common packet size. And they were running at 6 megabits per second. But subsequent work has designed these wireless mesh networks with auto rate algorithms running, and then applying COPE on top of it, and showed that you can deliver the same throughput gains. Yes.
So in the case of the analog network coding, the word router, of course, is a bit of a misnomer, right? It's really just broadcasting back. Would that affect how you designed it or how you implemented that piece of the network potentially?
So if you were only building analog network coding, then you need a very simple router. It's just an analog amplifier. But the way we look at this work in the future is thinking in terms of a cognitive MAC protocol. And what this MAC protocol is trying to recognize is that there are other degrees of freedom. You have a known packet, or you have another signal which you can use to decode packets. So the router has to take cognizance of this fact. He has to recognize that David and Sumit might already have some side information. So he should not try to decode these two packets. He should just amplify and broadcast it. So going in the future, you want these routers to make smart cognitive decisions about what to do with the packets they receive, what the signals they receive. So you need more than just a simple analog amplifier.
Can I go back to your coding and MAC gain when you talked about it?
Okay.
Yeah, so I had a comment. So in the beginning, so this technique it operates on the existing MAC, right?
Yes.
Okay, so perhaps using slots is a bit of a misnomer for dot level because although it's time shared, it's not slotted as such.
For 811, yes.
For dot level. The reason I say this is the example that you have, David and me communicating with the router in the middle explicitly assumes that David and I are out of are hidden terminals.
Yeah.
Correct?
Yeah.
So as you know, then the 802.11 MAC is not fair. The
Sure.
router is not going to get 1/3 of the time. So your work doesn't seem to take into account the fact that the router is not going to be able to, access the channel like the way you said it.
So for the theoretical analysis, so the question is, do we take into account the fact that these two nodes could be hidden terminals and the router might not get any access? So in that case, the coding gain is going to be even higher because the router is going to get even more congested. But in the actual experiments, we made no such assumptions. We let 802.11 run and do whatever it wants to do. So the results from the actual experiments have this hidden terminal scenario in its effect.
So my question is, although throughput may increase,
Yeah.
would fairness be exacerbated?
So fairness could be a problem, and that depends on how David and where these two nodes are located. And there has been parallel work which has looked at the fairness issues with 802.11 MAC and showed how we can use time-based approaches to get better fairness in this approach instead of using this random access method. But that is orthogonal to this work. Whatever MAC protocol you want to use, you can use it, and coding applies on top of it.
So it certainly seems like mesh networks have always been something that's just around the corner.
Yeah.
Could you comment on whether you think that these techniques are sufficient to get systems over the hump, or are there other challenges that also have to be addressed? In particular, one of the questions I had to do with the size of the system that you might run this on.
Sure.
That is, most of the techniques are really kind of very, very small scale, between a small number of nodes. But most of the deployments have been, or at least envisioned to be much larger, not just in the local area.
So the answer to the second part of the question is the algorithms are local, but they work in a global fashion. So like COPE is working at every router, and every router is trying to minimize transmissions. So the description is local, and that is actually good because you don't need global network information. But let me get to the more important question. Are mesh networks around the corner yet? And I think the answer to that is this was an important first step. It gave around a 3x throughput increase over many of these different traffic topologies and traffic demands. But there is still work to be done. There's still work to be done at the network level in getting more throughput out of this network and achieving the same spectral efficiency you would get from an 802.11 access point network. At that point, mesh networks are competitive because they have the same throughput guarantees which an access point network has and have the benefits of very easy deployment and blanket coverage. And I think at that point, you would see mesh networks out in the wild.
So you had mentioned something about the dynamic range of the ADC. And so that was interesting to me because I think it relates to maybe some practical questions that I would have, maybe coming more from the analog hardware side. What would you feel is the primary advantage of a mesh network as opposed to, say, just David communicating directly without the router to submit? So that's kind of the first part of my question. And I guess, let me just ask that.
Sure. So, I mean, if David is in range of Sumit and he can communicate directly, of course he should communicate directly, and that's what the routing protocol will do. But if they're not within range and they need a relay to assist them in their communication, they have to go through this relay to relay their packet to each other. So you need, to get the coverage and to get this end-to-end connectivity, you need the router to actually relay your packets.
I see. See, I'm not a networking guy, but I thought some of the promise of these mesh networks is that you could have these ultra low power radios and you could hop information from one to the next and work your way through the mesh for a longer distance. So the key word was their low power, right? So power is something that I didn't hear a lot of discussion about. And the reason I'm very interested in it is because all of the things that you're talking about, this analog network coding, it takes place in the MAC, correct?
Mm-hmm.
So that assumes that the front end of both the transmitter and the receiver preserves the signal, and i.e. we're talking, you kind of mentioned it, dynamic range, right?
Yeah.
So now if you start having these packets and they collide, so things like peak to average ratio of the signal itself will increase significantly. If you have two, then like you said, 3 or 4, start getting a picture. So peak to average ratio is going to really increase in things like phase noise in the synthesizer, dynamic range, the ADC, linearity of the transmitter receiver. They really start becoming part of the picture, and the power that they would require in order for you to preserve that signal under those conditions. I kind of wonder what if I just used a regular network and I did a brute force method for the same amount of power, or requirement, I guess. So everything I mentioned requires more power, right?
Sure.
So let's say for a given amount of power on these front ends for your system, I just did a brute force method. The power that I need to get this linearity, this phase noise, etc., for your system, instead of using it for your system, I just say, okay, we'll use the old network, inefficient network, and I'll just increase the modulation.
Yeah,
right?
so the question is really, what's the energy gains you get versus the amount of power I'm spending? What's the trade-off here I'm doing, right? And this slide is the answer. So the coding gain is a factor of 3. So you're reducing the number of transmissions in the network by a factor of 3x. Now, is the amount of extra power you spend enough, more than this 3x throughput gain you're receiving, because this is how many less transmissions you're already making. So I would argue that the energy savings you get from reducing the number of transmissions is going to be significantly higher than the amount of energy you need to spend to build these components. And especially because packet transmission is probably the biggest consumer of power. Running these radios itself is not that much power. And this has actually been analyzed by subsequent work once we published this paper, and I can point you to that work. So they have.
I suggest that this sounds like a wonderful longer discussion.
Sure.
So please let's thank Sachin again and wrap up. Thank you.
Thank you.